Now we turn to the programs, and I really am very honored and pleased to this afternoon to introduce to you 4 young engineers who have participated in our National Academy of Engineering Frontiers of Engineering Symposia, and they are recipients of what are called the Gilbreth Lectures. Now, these Gilbreth Lectureships, they are given to not only young engineers who have done very interesting and important things, but have a very impressive and important way of presenting them. So you're going to have great ideas very well presented from these 4 lecturers, and so this is a real treat designed just for you, as a matter of fact. These Gilbreth Lectures were established in 2001 by the Council of the National Academy of Engineering as a means of kind of recognizing young engineers who are just especially gifted in this presentation process. Now, our first presenter is a Professor Dennis Hong. He's a professor and founding director of the ROMELA, Robotics and Mechanisms Laboratory, in the Department of Mechanical and Aerospace Engineering at UCLA. His research focuses on robot locomotion and manipulation, autonomous vehicles, and humanized robots. He is an inventor of a number of novel robots and mechanisms, including whole-skin locomotion. You have to tell us about that, Dennis, whatever that is. For mobile robots inspired by how amoeba move, a unique 3-legged walking robot called Strider, an air-powered robotic hand called Raphael, and a world's first car that can be driven by the blind. I'm not sure driven where exactly, but that's very... Dr. Hong received his BS degree in mechanical engineering from the University of Wisconsin at Madison, MS PhD degrees in mechanical engineering from Purdue University. The title of his talk is Biologically Inspired Mobile Robots. Dennis, the floor is yours.
Okay, good afternoon. Again, my name is Dennis Hong. I'm a professor at UCLA, the Mechanical Aerospace Engineering Department. I'm the director of ROMELA, the Robotics and Mechanisms Laboratory. And today, I would like to give you a quick presentation under the title, Biologically Inspired Mobile Robots. So we're going to be talking about really cool robots. So if you look at the screen over here on the left-hand side, there's a lot of robots, and probably you recognize some of them, like the iconic Honda Asimo, or Charlie robot and Darwin robot that actually we developed in our lab, Mars, Heads-Up robot, and the PackBot, which is actively being used in the military and also for disaster relief applications. The exoskeleton suit and the ubiquitous robotic manipulator arm, which most likely your car is actually assembled by these type of robotic arms in the factory. But all of these robots are fundamentally different from their biological counterpart. They might look similar, but look at the animals on the right-hand side. These animals in nature are just remarkable. Their performance is just incredible. Think about the performance of the speed and agility of the running cheetah, or a swimming dolphin popping out of the water, or even the gecko climbing a wall with its bare feet, and even the bats flying in the obstacle field in the dark in the night. It's remarkable. So what really makes these animals and the robots performance different? So for example, most of the robots of today, we use, for example, in terms of materials, we use hard materials like aluminum, steel, titanium. The biological animals, they use flesh, very compliant materials, or even, let's talk about actuators. Robots use electric motors or sometimes hydraulic systems, but these animals use biological muscles, and these muscles are fantastic. They're energy efficient, they're compact, and they're brilliant. So naturally, we in the research community in robotics, we try to look at nature and try to learn from nature and apply these biological principles to robotics. And that's what we call biological inspiration in robotics. So robotics is a very wide field. You need mechanical engineering, computer science, computer engineering, electrical engineering, all different fields. In particular, we need to do modeling, control, you need sensor and electronics, you need actuators, material design. All of these are needed. And more specific, in modeling, we need to learn how to do rigid body dynamics, kinematics for feedback control, different type of mechanical elements, and you need all of this, and only when you can put this all together successfully, you can develop these type of robots. As a matter of fact, I call these the classical robots. These are the robots of today. Now, something interesting happens when you try to start to injecting biological principles to this big picture. So we look at nature, we study nature and biology, and we apply the principles, and then something interesting happens. All of these details now slightly changed right now. So modeling, now we're looking at continuum modeling. For control, we're starting to look at stochastic control. Materials, soft materials, compliant materials. biomimetic sensors, actuators. Now, instead of these position-controlled servo motors, now we're looking at compliant, we call these impedance control, series elastic actuators like artificial muscles. And then when you put this all together, there's a new field called biologically inspired robots. And this is enabling us robotics to come up with novel robotic systems. And by nature, this is a multidisciplinary research. So what is biomimetics? Well, if I may define it, as it says, it's seeking design solutions from nature to replace the classical engineering solutions that we currently have. Now, biomimicry in robotics covers everything, not just the structure, not just the materials and actuators, but also the intelligence and everything. But in today's talk, I would like to focus more on the mechanical and the mechanism design for mobile robots that run on ground. So I'm not going to be talking about flying robots or swimming robots today. Now, one interesting thing is, when you design robots using biomimicry, oftentimes the robot that you develop does not necessarily look like its biological counterpart. Sometimes it does. Let me give you some examples. Now, these two robots are two humanoid robots that we designed in our lab. The one on the left is called Charlie. The one on the right is Sapphire and Thor. Depending on which application you use, they have two different names. These are humanoid robots, which means that it looks like a human. 2 legs, torso, head, and 2 arms. But the one on the left is not truly bio-inspired. It looks like a human, but not the principles necessarily. But the one on the right-hand side, we actually studied biological principles and we tried to apply it. And then the performance is very, very different. Let me give you an example. So this robot, Charlie, stands for Cognitive Humanoid Autonomous Robot Learning Intelligence. It's more of a classical robot. All the design, fabrication, analysis design is done, everything in our lab. It uses more of the classic gears, pulleys, and servo motors. The performance is actually pretty good. It walks about 0.4 meters per second, is omnidirectional. It has built-in artificial intelligence. The camera looks around, tries to identify the world and build a world model, and can do many things. However, this robot can only walk on smooth, hard, even surface and not for unstructured environments. We use this robot for many things. I included another video just for your entertainment. We use this robot for many things, including a competition called RoboCup. Anybody heard about a competition called RoboCup? Yeah, it's International Autonomous Robot Soccer Competition. So we build robotic soccer teams and play soccer. This is not remote control. Everything is fully autonomous. Let me quickly show you. So look at its head. So he's looking around. He's searching for the ball, looking at the lines, trying to figure out where he is. He dribbles the ball to the other side. And again, he's doing everything on his own. We're not remote controlling it. And he's trying to kick the ball into the goal.
Yeah, come on, Charlie. You got this. Let's go, Hokies!
Yes! I mean, let's face it, it's not Ronnie. It walks like, and it doesn't kick like a soccer player. It barely kicks the ball. But you can see this excitement because to develop a robot, a humanoid robot walking with 2 legs, everything autonomous, you really need to solve all the grand challenges in robotics. Robot vision, dynamics control, design, autonomous behavior. Only when you can do all that and successfully put it together, you can build this kind of robots. And that's why we're so excited. However, as I mentioned, by the way, so we are 4 times world champions in RoboCup. Yes, that's the famous Louis Vuitton Cup Baccarat Crystal Trophy that exists, only one exists in the world. Next time, invite me again, I'll give another talk about RoboCup. It's very exciting. But as I mentioned, this robot, though it's very impressive, it's not really, look at how it's walking. Do you walk like this? No, this is not really how we humans walk. Going into more technical terms, we call it ZMP, zero moment per walking, but it does not walk like humans. We just built a robot, we use brute force control to make your robot walk with 2 legs. So if you really want to use these robots in real situations outside the lab in unstructured environments, these robots need to tackle the uneven terrain. So we're starting to look at nature to get inspiration. This is a robot called Sapphire, shipboard autonomous firefighting robot that's funded by ONR, the Navy. And we're developing a robot that can fight fires on Navy ships together with the firefighters. Now for this is a significant departure from the traditional humanoid robots, if I may say. So those red things, these are new type of actuators. It can say it's a artificial muscle, but the more technical term is a series elastic actuator. In the past 30 years, we roboticists try to get rid of the springiness of the joint. We want to have rigid, accurate motion control for assembly tasks. But now, working with biologists, we're starting to understand the importance of compliance or springiness like biological muscles. So we developed these new type of actuators, and then it's walking in the lab. Not only it walks, but it can do many, many things. Because you're using these new type of principles, it's a new type of actuator. For example, if you look at the robot structure, it looks very different from the traditional robots that you see. You use these parallel actuation schemes with the series elastic actuator. It has a full range of motion, just like a human. I'll talk more about why we need this too. So it has a full range of motion as a human. This robot, by the way, this robot is called Thor. We're using it for disaster relief applications. And this might not look very impressive, but for those who know about robotics, this is very impressive. We're doing impedance control. So we can change the impedance and control the force. So if you put it in zero impedance, it just moves like a pendulum. And because of this, these robots behave very differently. Just like a biological muscle or an animal, it's compliant. And because of this, it will be able to walk on uneven terrain, climb structures, steps, and even the ground is moving. The performance is remarkable. So this is a very different paradigm in humanoid robots that we're investigating. So you've seen the difference between Charlie and Safra and Thor. The one is we designed the robot first and tried to control it. Safra and Thor, we tried to understand biology and try to apply to that to come up with different things. As I mentioned, biologically inspired robots does not necessarily look like their biological counterparts. So because we're not just copying the robots, we're studying the principles and applying them. This is another good example that we do. It's a robot called Strido, self-excited tripedal dynamic experimental robot. It's a robot that has 3 legs, but it's inspired by nature. Isn't that weird? It has 3 legs. Have you seen anything in nature that has 3 legs? Probably not. So why do I call this biologically inspired? Before that, let's look at pop culture. H.G. Wells' World of Worlds, a novel and also in a movie. And anybody recognize this? Video games? Half-Life 2? Yeah, they describe this like alien creature that has 3 legs that terrorize Earth. However, our robot Strido does not walk like this, and it's not built for this purpose. Now, if I click this clicker, it's going to show you a dynamic simulation of this, how Strido is walking. Now, before I click this, can everybody tell me, can you think of how this robot might walk with 3 legs? How do you think it's going to walk?
It would stand on 2 feet and turn entirely.
Oh, turn this way. Yeah, that's a very cool idea. Let's write a research proposal together and submit that. Cool. What else? Yeah, just shout out. Yeah.
I think the back leg go like extend forward and the 2 legs will just walk like.
Oh, like this, like R2-D2, right? Oh, that's cool. Yeah. What else? Jump around. Oh, spin around. That's also a cool idea. All right. So let me show you how this walks. So when I click this, when I go to robotics conference, I show this video to my colleagues, and everyone goes like, "Ooh, wow!" So when I click this, everybody say, "Ooh, wow!" Okay, let's see. Ooh, ah, whoa! Isn't that cool? Wow. So what's happening is it's falling forward, and the middle leg swings the leg between the 2 legs and catches the fall and stands up again and repeats that. So again, all my robotics colleagues see this, like, whoa, and then after like 10 seconds, they say, "Dennis, why are you trying to do this?" Because it's cool? Yes, it's cool, but there's a good reason why you're doing this. Now, this is very energy efficient. I told you this is a biologically inspired robot. As a matter of fact, we study how we humans walk with 2 legs, and we try to apply that mechanics to this robot. It doesn't look like anything like a human, but this is more closer than, for example, Charlie robot or some of the human robots in terms of walking like humans. So we call this the principle of a passive dynamic locomotion. We just don't lift our leg, put it down, lift our leg, but rather we swing and catch the ball. When you stand up, potential energy, kinetic energy. So that's what we study and try to apply, and we get these incredible robots. So I've been working on this robot. This is the first time for a successful step. We're building a 10-meter, 3-story height version called Taller right now in our lab. So if you look at nature, there's many, many different ways the animals walk. So there's many reasons why they do that. For example, we humans build machines. Let's look at our cars. Cars use wheels. Have you seen a car that use legs? Probably not. Look at nature. Have you seen wheels used on animals? No, they use legs. Humans use 2 legs. Most of the animals use 4 legs, or insects use 6, or many, many legs like a centipede, or sometimes no legs like a snake that generates this wave-like motion. Why do you think we humans use wheels? Or it's very, very efficient. It's great. Let me change the question. Why do you think nature does not use wheels? Difficult. Yeah, there's many, many reasons. You need to have these nerves and all the blood vessels going through, and if you have a continuous rotation motion, you cannot do that. Those are good reasons. Another good reason is because the actuators are different. The locomotion method changed because In general, in nature, they use muscle, which is by nature is a linear motion. We humans use engines and motors. That's a rotational motion, so naturally we do that. Size matters too. Like for example, when there's danger, these animals need to quickly, move away, need to escape. Small insects like fleas, what do? They jump. Right? That's because these small animals, because of their small size, it's very difficult to move fast, so they jump. However, large animals, they run or crawl because of their size, jumping is very inefficient. So because of all these different factors, animals move in different ways. So what we do, robotics, is we just don't make a huge jumping robot because we want to. We study and try to understand the science behind the biology and the animals, and we try to use that knowledge to develop robots. So these are a series of robots. These are jumping robots developed in the past decade from research labs from all around the world, and they're all inspired by these animals in nature, from flea to grasshopper and locust, all these things that jump. So we study the mechanism, how they do it, and they apply to robotics. And look at these robots. Do they look anything like the ones on the top? The scat robots look like a big cylinder, and it looks weird, right? So these are some good examples about applying the principles of biology to robotics. Let's talk about walking robots with legs. This is a robot that we developed together with NASA JPL. This robot is called MARS, Multi-Operating Robotic System. We're trying to look at how to use your compliance or springiness in the joints to tackle these type of uneven terrain. Some other robotics work from other labs. This is from Berkeley, Ron Fearing's work. Let me just show you the video.
The design of Dash has been informed by the study of nature's greatest runners. From these animals, scientists have derived many models
What animal
for
is
robust
that? The
high-speed
cockroach.
locomotion.
Remarkable animal. Also cute. No.
Dash is constructed using a scaled smart composite manufacturing, or SCM, process.
So this is also
that
about
creates
new
rigid
type of
cardboard
manufacturing
beams with polymer
methods.
flexure joints. Laser micromachining removes cardboard from the flexure joints in a mirrored pattern. A thin polymer is laminated between the mirrored cardboard sheets, and then the final outline cuts are made. The cardboard beams and flexure joints
Okay,
can
I'm
be
going to skip
folded.
the video. There's a lot I want to show, and we're running out of time. So,
Dash is able to run straight at speeds of
does look
1.5
like a
meters
roach.
per second, or 15 body lengths
so these
per
are some of the
second.
results by
And
studying
video slowed.
nature, in this case, cockroaches. This is another robot. It's a much smaller one from the same group from Berkeley. So they can make these smaller robots too. All right, let's talk about worm-like crawling. There's many different ways that worms actually move. This is called peristaltic crawling. So what it does is it changes diameter continuously to generate this kind of wave-like motion. So Roger Quinn's group studied this and tried to synthesize a mechanism that moves like this. And the result is this. It has a single motor with some clever cable pulley mechanisms. It generates that wave-like motion that changes the diameter and it moves like a worm, though it's a much bigger worm that you might expect. If I meet something like this on the hallway, I'm probably going to run away. But it's very cool. Worms also, this is a smaller version. This is from MIT, Seok-Sang-ok and Sang-baek Kim's lab.
Specifically, the earthworm for design inspiration. They noted that the ground dweller is made up of two main muscle groups that work together to inch the worm along. Researchers created artificial muscle from wire made of nickel and titanium, a shape memory alloy that stretches and contracts with heat. They wound the wire around the tube, creating segments like that in an earthworm. They then applied a small current to the wire segments, causing the wire to contract and squeeze the mesh tube, propelling the robot forward. As an ultimate test, the group subjected the robot to multiple blows with a hammer, even stepping on the robot to check its durability.
That's my favorite
The
part.
robot proved remarkably resilient, surviving the attacks and crawling away intact. Kim says such a
Yeah, so other worms walk in different ways. This is called a two-anchor crawling. So sometimes the worms have the grasping thing in the front and the back. So it grasps on the rear, the body stretches and grasps again and moves like this. So researchers try to implement these type of things in robotics. It's very effective at climbing. It can also handle a pretty heavy load. In this case, 1.75 kilogram payload, and it's climbing a tree. This is another miniature version using shape memory alloy. This is from Seoul National University by Cho Gyujin. Oh, this is kind of cool. So sometimes some worms, mealworms, when they encounter danger, they can do this ballistic rolling motion. Right? And then the researchers studied these and they tried to mimic this, and they came up with something that looks like this. called the Go Qbot. Go. There you go. Bye-bye. Talking about snakes. Snakes move in many different ways. This is from Shigeo Hirose.
This robot moves by twisting its body similar to the motion of a snake.
Not only it rolls or
motion
slithers
is
on the
almost
ground,
the
but also
same on
underwater.
land and
It's
in
very,
water.
very lifelike. It's pretty impressive.
One feature of this robot
Or from Howie Chose's lab from CMU, very well known for robot snakes. Now, these snakes move in many, many different type of ways. Some are biologically inspired, some are not biologically inspired. I tried that once, it feels really weird. And it goes on. So I also developed a robotic snake called Hydrus, Hyperdivisa of Freedom Robotic Articulated Serpentine. This is actually not biologically inspired, but it wraps around the structures and it changes the oscillating motion of the joints to a whole body rolling motion. So it can climb up, climb down structures, for example, used for bridge pier inspection or for construction sites. All right, so this is kind of interesting. So talking about the whole skin locomotion, since you asked. Since I was a kid, I've been fascinated by biology. I didn't formally major in biology, but since I was a kid, you know, you look at the TV documentaries and those kind of things, and I've been fascinated by single-celled organisms in particular. These single-celled organisms move in one of the three ways. They have a flagella, like a tail, or cilia, these are vibrating hairs to swim, or pseudopods, like a amoeba. And I'm interested in ground locomotion. So since I was a kid, I always wanted to build a amoeba robot. And this is actually a video clip of how an amoeba moves. It morphs into different shapes. And I wanted to build a robot that moves like this. It's just like anybody seen the movie Terminator 2? Liquid metal robot? Yep. So that's the robot I want to build. If you want to build an amoeba robot, what do you study? You need to study amoeba, so that's what we did. So what we found out was how an amoeba moves, and this is fascinating. I know we're running out of time, but I need to explain this. So a real amoeba moves like this. The inside is called endoplasm, it's a liquid. The outside is called ectoplasm, it's like a elastic skin, jelly-like skin. For the amoeba to move forward, what happens is the endoplasm flows forward, and something interesting happens on the front. There's a liquid to gel transformation, so it actually builds its skin. Isn't that cool? But what's more interesting is in the back. The back skin liquefies and gets absorbed back into the body. Wow, this is really cool. So in other words, a skin particle is stationary until it hits the back, then it gets absorbed to the body, floats twice the velocity, and then it becomes the skin again. Aha, now we know how an amoeba moves. Now we just need to make a robot. But how do you do this? So after a month of brainstorming, what we came up with was this. You've probably seen this. Do you have one? They sell it in a toy store. It's called a water wiggler or water worm, right? And people say, hey, you cheated. There's no liquid to gel, gel to liquid transformation. True. But if you look at it, the general topology is exactly the same thing. So this is our solution for this amoeba robot. So before I talk about how it moves, why do we need this? For example, a building collapses, you need to send in rescue robots. Wheels cannot go, legs get caught. If you have something like this, it can squeeze between obstacles, squeeze under a collapsed building. If you can make it really small, we can also use it possibly for medical applications like endoscopes and things. Since it's a very new type of way of moving, we didn't want to use your classical gear pulleys and those kind of things, but rather those rings are actuation rings. They expand and contract, and if you embed that into the elastic skin, as they contract in sequence, it pulls the skin inward and pushes the skin outwards. So we do a lot of experiments by storing potential energy to the skin to make it go forward. Going backward is the film rewinding. We use active tension codes to make it go forward and backward, and we're doing a lot of interesting things with this. We also investigate how to do it with rigid bodies. We call these Kaliode-cycles, 1 degree of freedom everting mechanisms. Does anybody know what that yellow thing is? You have it at home? Tape measure. I'm sure you play with a tape measure. When you buckle it, it bends, right? If you do something interesting happens. But have you thought beyond that? What that is actually a new type of joint. It's a combination of a rotary joint and it's a traveling, with a linear joint, it's a traveling revolute joint. So using that principle, you buckle it twice to make this a loop, and using shape memory alloys, if you heat one side, it actually moves. So that was the first working prototype. So we do a lot of things. We're running out of time, so I'm going to skip all this. It's actually going through a hole smaller than 1/3 of its diameter. It actually flips to the other side. And based on that, this was a project called Chembot or Chimera. It's freaky. It's all chemically actuated robot. No batteries, no actuators, and it moves just like magic. So these are some examples of things. Now, what's the future of biological inspired robots? There's a lot of, it's a very exciting field. Among the many things, including soft actuators, I believe that soft robotics is something really cool. It's an emerging new thing. These are some examples of soft robotics examples from different labs around the world. You can see that the whole body is soft, and there's no concept of link and a joint. The whole body is moving. This uses compressed air. That's a robot octopus. And the whole thing moves. So there's a big future for soft robotics, in my opinion. Soft robotics is exciting. You need to figure out, there's a whole open field that we need to do research. So these soft body robotics has infinite degrees of freedom, or really, really large degrees of freedom. How do we actuate this with discrete number of actuators? This actuation motion is combined together with the structure itself. How do we make it move? We need to take advantage of different type of characteristics of the nature of the soft body, like bistability, buckling, and those kind of things. And how do you make these things? I personally don't think these soft robots will replace all the robots, but they're going to have specific applications such as medical application and different things. And it's a very, very interesting, new, exciting field. I think we're running out of time, so I think I'm going to end over here. So thank you very much. Question, yeah. Okay. So if you have any questions, I'll be more than happy to try to answer or have a discussion. It doesn't have to be about robotics. It could be engineering or anything. Yes. Please.
With AI advancing, do you think we should have some safe fails in case it all goes out of hand as established by Isaac Asimov in his books?
Yes, the question is about the danger of AI. So this has actually been a very hot topic recently. Elon Musk made a comment. A lot of prominent engineers and scientists, people made some comments on AI. Now, disclaimers, I am not an expert in AI. I do use AI. I'm more of the end users. I collaborate with different researchers in AI for our robots too. So even researchers, everybody has a different thoughts. My thought is, the general public, we have too much high expectations about robotics. We watch science fiction movies, you see robots. So for example, we have students, kids come to our lab, we show demonstration and go like, wow. And after about 1 minute, they say, why can't it do that? Why can't it lift the car with us? Why can't I run around? I tell them, oh, no, we don't have that technology, but we're working on it. And they say, no, I've seen it last week on TV, right? So the expectation is too high. AI is another good example, in my personal opinion. So AI also means different things depending on who you talk to. For me, as a mechanical engineer who develops these type of robots, if you ask me what AI is for me, autonomy is artificial intelligence. Like for example, I showed you a lot of the robots. If you give a higher level task, robot, open that door. Robot figuring out what's the door, how to get there, how to open the door. That's AI for me. But the question that you're having is the other side of the AI, more of the philosophical, ethical question. So I don't have the answer for that, but as an engineer and scientist, it is very important to think about this. I always teach my students that we should always consider the impact of our work that will have in society. So it's a very important thing to worry about, think about right now. But I think personally we have a long way to go until we reach that point. But it's good to think about it right now. Question? Any other question?
How did you become an engineer? Like, what made you interested in building robots and stuff like that?
Yes, true story. When I was 7 years old, I watched the movie Star Wars for the first time. Episode 4, not 1, 2, 3, episode 4. That's the real Star Wars for me. I was fascinated by all the spaceships and everything, but among them, you probably know R2-D2 and C-3PO. I was fascinated by that. I was 7 years old, and that was the coolest thing. At the time, I didn't know what the robots are for, how to build a robot, but on my way home in the car, I told my mom and dad, Mom, Dad, I'm going to be a robot scientist when I grow up, and I never lost my dream, and I'm here today. I followed my dream, and that's what I'm doing right now. Yeah. So instead of taking a question and answering, I want to tell you just one thing because we're at NIA. So, I mean, there's going to be future scientists and engineers here. Engineers, we are superheroes, right? We're using math as a language and science as a tool. We solve problems. In my case, we're developing robots that will save lives. The firefighting robot. The robot Thor is actually used in a competition called the DARPA Robotics Challenge for disaster relief. 4 years ago in Japan, what happened in Japan? There was the very unfortunate nuclear power plant accident, Fukushima Daiichi. But actually, as a matter, last year I was invited by the Japanese government. I actually went inside the nuclear reactor. That's a different story. But we're developing robots that can be used in these kind of situations. So what we're doing really is to truly save humanity, and that's what we're doing. So engineers are cool. You guys will be superheroes. So there you go. Thank you.
Great talk, Dennis. Well, Dennis, thank you very much for your talk, and we have here a special presentation for you, and I'll read this. Is it all right if I read this?
Oh, please.
Yeah, this is a certificate from the National Academy of Engineering Armstrong Endowment for Young Engineers Gilbreth Lecturers to Dennis Hong, and is hereby honored as a recipient of the Gilbreth Lecturership in recognition of outstanding contributions to the field of robotics and presentation of his lecture on biologically inspired mobile robots at the National Academy of Engineering 2015 National Meeting. Dennis, thank you very much.
Oh, thank you so much. Thank you.